so let us, I say that probably at the beginning of every video, don't I? Let us continue along our thermodynamics adventure. Let's skip that example. Okay, let us now start our way into chapter 5. Okay, so that's going to be our goal now. Let's get into chapter 5, introduce some concepts, and lay down some theories so we can go pretty fast then when we jump into the next lecture. Chapter 5, the first thing I've got there is conservation of mass, because when we look at chapter 5, lecture 10, this is page number 2, this is lecture 10, this is page number 3. So chapter 5, it deals with first law for control volumes. Again, for us in the Chamberlain-Bowles text, that is chapter 5. Now, what is a control volume? Now, if you don't know what a control volume is, please pause it and go look this up in your notes. I will wait. Okay, you know what a control volume is. Good. And the difference between a control volume and a closed system. I hope you figured that out as you were going along, or if you don't already know that. Okay, that's okay. I'm going to leave that to you to figure that out. So when we start talking about control volumes, we've also got to worry about make sure that the mass is conserved, because now I've got both mass and energy crossing the boundary. So mass has to be conserved through the conservation of mass principle. And that's just simply saying that, kind of like the conservation of energy principle. Mass, like energy, cannot be created nor destroyed. We won't even say it can only change forms. I mean, it kind of does, but the exception, of course, would be a nuclear reaction, and we'll leave that to the nuclear engineers, which we're not going to cover in this course. If you're going on into that, congratulations, have a good time. That's not what we're doing here. Okay, so but we do need to keep track of the conservation of mass, okay, and make sure that it's being conserved mathematically. So what does that mean? Well, if we look at the conservation of mass, that simply says that if I add up the summation of all the mass flow rates coming into my system minus the summation of all mass flow rates going out of my system, that equals the change in the mass of my system with respect to time. Maybe that sounds and or looks familiar, right? All of the in, subtract all of the out, equals the change. It's a conservation law, just like conservation of energy says in minus out equals change. Conservation of mass says in minus out equals change. Okay, so that's by design. That's on purpose that it looks the same, because there's a lot of similarities. I'm putting summations here because there could be more than one place where mass comes into a system. There could be more than one place where mass goes out of the system, and we've got to keep track of all of it. Okay. Now, as we've discussed before, I think we introduced the concept of a mass flow rate in chapter 2, and we said, well, that could be density times the volumetric flow rate. Again, a dot above a variable means it's per unit time. So mass per unit time is equal to density times volume per unit time. This is mass per volume times volume per time. That gives me mass per time. And again, how does one find the volumetric flow rate? Well, you can stand out there with a measuring cup or a graduated cylinder, and you catch the liquid as it comes out of the conduit. You measure with a stopwatch the volume over a period of time. That's one way. That's not really practical. That normally doesn't work. What you can normally do is you can say, well, if I take the product of the cross-sectional area, the cross-sectional area of the conduit multiplied by the speed, the average speed of flow. The product of area and speed will give you, this is area times length per time, so this is length squared times length per time, that's length cubed per time, that's volume. So area times speed gives me volume per time. And again, remember, we've got our friend, the specific volume, that is the reciprocal of density. So anywhere I've got density, I could also use the specific volume. Specific volume, very handy when I'm talking about vapors and gases, because it's a larger number. Density, pretty handy when I'm talking about liquids, because it's a larger number. But either one works in either case. Okay. So, now, if we talk about a subject, this text calls it steady flow. AKA many texts, so also known as, many texts and branches of engineering will call this steady state. You'll hear that a lot of times in chemical engineering, steady state. Your scientists, physicists may call it, refer to it as equilibrium. Right? That's where everything with respect to time is constant. There's no change with respect to time. Okay? Steady flow, what that means is, in any device that we're going to encounter, we acknowledge that there's probably going to be this warm-up or a cool-down period after it operates, where it's basically kind of getting up to speed, or it's warming up, or it's filling up. We don't have it operating perpetually, so to speak, or at a steady rate or steady flow pace yet. Now, once it reaches that point, once it gets to a point where we could operate it as long as we can feed an input to it and maintain the output, then we reach this, what we call steady flow condition. And once we reach this steady flow condition, that's where we're saying everything is constant. Right? There's no change over time. No noticeable change over time. It's going to operate perpetually. It's not a perpetual motion machine. We have to provide the outside input. But as long as we provide the input and can maintain the output, the machine will operate the same way as long as we can maintain that. Okay, that's what we call steady flow. One of the best examples I can think of that most of us can relate to, I always say, think of a garden hose on a hot day. So if you go outside and you turn on a garden hose, right, you hook up a big long garden hose up to your faucet, you turn it on, you run, you grab the other end of the hose, and as soon as you turn the faucet on, is there water coming out of the other end? No. As soon as you turn it on, there's a period in time where you've got a lot of mass, you've got a ton of, like a whole bunch of water, heavy, massive water coming in, and you're pushing a bunch of air out. So there's a period of time where this is larger than this, and so there's a period of time where the mass of that garden hose is changing over time, until you reach the point where you've got as much mass coming in as you have going out. Basically, when you get as much water going in as you have water going out, you get all of the air out. You fill it up. Then this approaches zero. This reaches kind of a 0 point. This reaches a steady flow point. Now also, think about the energy. So on a hot day, if I turn on the water faucet, and even after I start getting water coming out to where this approaches 0, right? So even after I've filled this thing full of water to a point where I've got as much mass coming in as I have mass going out, and if it's a hot day outside and you touch that water that's coming out, that's hot, right? In fact, there's scary pictures right now on some social media about, you know, little kids getting burned because it's not. I'm sorry, I shouldn't laugh. It's not funny. But there are like people and kids getting burned by this hot water coming out of the end of a garden hose because it's been sitting out in the sun. You turn it on, and that water comes out really hot. There's a period in time where that garden hose itself, the system is the garden hose. There's a period of time where that garden hose is going to be cooling down over time. So there's a period of time where even once the mass stabilizes, the energy may take some time to stabilize. So there'll be a period of time where the energy of the garden hose itself, the internal energy of the garden hose, is going to be decreasing over time. But after you run that garden hose long enough to where you get a constant temperature or a constant internal energy coming out of the garden hose, and it might be higher than the internal energy going in. There might be enough heat from the sun to heat it up between the beginning and the end of the hose, not much. But you will reach a point where you reach this steady flow to where this doesn't change over time. Okay? So, again, the big thing there is for steady flow, you reach this point where the sum of mass, the total mass flow rate in, is equal to the total mass flow rate out. And you could write the same thing for the energy. I'm going to write the energy this way, though. I'm going to write it a little different. I'm going to say the total rate of energy in minus the total rate of energy out is equal to 0. If we have what we call steady flow, and again, if you're joining us and you're learning from another text, your text may refer to this as steady state. That's how I learned it. That's okay. This text likes steady flow. So we'll use steady flow here. Okay, and we're talking about the same thing. Okay, now that's important because if not, notice that both of these are differential equations. And again, I'm not assuming you've had differential equations yet. And even if you have, you may only have rudimentary tools to do anything useful with these. But notice what happens when these go to 0. If we can say, hey, the system is flowing steady, let's just worry about this. Let's not worry about startup. Let's just worry about once this thing's going, what does it look like? And if these differentials go to 0, then this is pretty easy to work with algebraically. And that's kind of where we're headed with this chapter. This chapter 5 is down this path. Okay, what else we got here? The energy of flowing mass. E dot mass in and E dot mass out. Okay? So let's talk about those energies. The energy of mass coming into a system and the energy of mass going out of the system. The water in my cup right now, the water in my cup has what types of energy? Right now, water's sitting in my cup. What types of energy do we have? Once it settles down. Well, it has internal energy. Right? We know that. Now, in theory, it has kinetic and potential energy. It's sitting on top of my desk, which is above the floor, which is above sea level, which is a long distance to the center of the Earth. So there is potential energy if it's allowed to drop somehow. It is moving, just it's moving at the same speed my table is, which compared to me, it's not moving very fast, but compared to the sun, the surface of the sun, it's moving very fast. So it has its own kinetic and potential energy. It's just, it's not really doing anything right now. And it has its own internal energy. Those molecules are moving around right now. Okay? So we'll pick up there on the next video, and we should be able to finish up.